¿Está?
¿Está grabando?
Sí.
Es importante.
Listo, ahora podemos empezar. Después de todos los problemas técnicos.
Bueno, yo primero voy a empezar con un agradecimiento que no son a los homenajeados de acá, que es Andrea por haberme invitado a decir algunas palabras. Y yo decía, bueno, de parciales, squares, regression, ¿qué puedo decir yo? Nada, por supuesto. Pero, bueno, más allá de las palabras un poco por ahí institucionales que son importantes usar en estos eventos, como decir, hoy es un honor, es un orgullo y demás, uno se ve tentado a usar ChatGPT para decir que les haga rápidamente un discurso de lo que uno quiere hablar, y siempre el resultado es pésimo, por lo menos de acuerdo a mi experiencia. Entonces dije, bueno, en realidad yo lo que quiero decir es lo que siento. Y yo lo que siento es una alegría por un hecho consumado que es un trabajo, en este caso plasmado en un libro que llevó adelante Liliana con Dennis en Estados Unidos, que debe haber sido más o menos como caminar hacia la cima de una montaña, se llega a una cima, ¿no? Probablemente muchos contratiempos en el medio. Ustedes saben que es como escribir un paper, pero es mucho más que escribir un paper. Es proponerse trabajar sobre una idea que tenga un impacto sobre distintas comunidades. Una de las comunidades que creo en la cual ustedes han prestado o se han inspirado son los quimiométricos. Acá lo tenemos a Fabricio, en algún momento, no tanto ahora, pero Marta, Marta la traje yo de público, que ha trabajado en estos temas. Y es que, bueno, ese trabajo, ¿no? Desde una disciplina particular de estadística es ponerse a mirar cuestiones que otros, desde otros lugares, desde otras disciplinas, desde la química o desde la física o lo que sea, se han puesto a usar herramientas, estas herramientas han dado buenos resultados, pero por ahí yo como químico, bueno, uno lo usa como herramienta, pero no conoce los detalles o las implicancias de esas herramientas que está usando. Y el hecho de que haya gente que son las que desarrollan realmente las herramientas y las que conocen los detalles, se pongan a trabajar y presten atención a este tipo de cosas de tal manera que se pueda trabajar en forma conjunta entre distintas disciplinas, creo que es esencial. Y para hacer eso se necesita gente trabajando fuertemente en esas disciplinas, en cada una de esas disciplinas. Entonces creo que, bueno, este libro, un poco que es el resultado de este trabajo entre Liliana y Denis, entre dos personas que vienen trabajando fuertemente y muy apasionadas con lo que hacen, para mí es realmente es eso, ¿no? O sea, constituye una alegría como integrante de la comunidad, por supuesto como decano de la facultad, y que se repita, que haya más de esto, aunque es mucho esfuerzo, ¿no? Así que bueno, lo que yo puedo decir es gracias, básicamente. Gracias por el trabajo.
Okay.
Ahora pasamos al inglés.
I'm perfect English. If you don't understand something, you can ask me.
Yes,
yeah, from outside. Good morning, good afternoon, evening, wherever you are. I'm Liliana Forzani, you know me, and I'm the co-author of this book that I did. We published with Dennis just a few months ago, and it's my turn to introduce Dennis. He doesn't need introduction because everybody knows Dennis Cook, but nevertheless, here I am. I will give an introduction. I always thought about myself, I'm a very generous person, but until this year, I realized something. I never invited Dennis to give a talk here at my university. Before the pandemic, it was like natural, but after that, it was from the pandemic that we have thousands of talks through the Zoom. There was no real excuse not to invite him. And I think it's because I was not generous. I wanted Dennis' knowledge all by myself. Well, once I realized, in fact, was Andrea's idea, I invite him, and I'm sharing Dennis with all of you.
Thank you.
Dennis is known for so many contributions to statistics, like Cook's distance. Then today, Dennis, and an honor to you, I show the proof to the mathematicians and data science students in my matrix algebra class. They were learning today the proof of the Cook distance. And of course, he did a lot of work in regression. But I want to say something about Dennis that I think impact me a lot. Dennis was a professor. He's a professor who has always the door open, meaning you can go and ask him something anytime. Except when he was teaching, once I was there, he was teaching Monday, Wednesday, and Friday, he was teaching his regression class from his book that he wrote, and a lot of the material was done by him. But after 10 a.m., you couldn't disturb him because he was preparing the class. And this is for me, I was amazed by that. Now, he was preparing the class. He was stopping doing research to prepare the class about material that, okay, he knows more than anybody. After that, teaching was never the same for me. I'm a lucky person. I still work for 20 years with him, and I still enjoy working with him, learning new things, and realizing he's always thinking about new projects. Like the book he's going to tell you about today, and I'm hoping he really retires soon because I want to retire too. Well, thanks, Dennis, for giving this lecture and for the opportunity to talk with you, to work with you in so many long and demanding projects. Okay, here is Dennis. Dennis, you can talk now. You can share the Facebook person, please. Dennis, we cannot hear you. Again.
What's that? Can you see that? Francesca's nodding her head, so I assume that's
Yes, yes.
Okay.
So
well, thank you for that introduction. I think I seem to miss about every third word, but I got the general gist of it. I've been studying partial least squares now for about a decade. I started this for two main reasons. One is that I was just academic curiosity. What is it all about? It seemed that not many statisticians knew much about, if anything, about partial least squares, and yet partial least squares is a method that was then and still is used widely across the applied sciences, particularly in chemometrics. So the second issue was to try and find out if there was something here that they should know about, and maybe understand why statistics, why this didn't carry weight, evidently in the statistics community. When Lily invited this talk, I thought it would be easy. Well, I'll just go through our book and pick out a few of my favorite topics and then discuss those, and that would be the end of it. But it turned out to be quite hard because I liked everything in the book, and it was hard to try and pin down a few things that I hopefully get across in the time of a normal seminar. What I decided to do is focus on those that connect partial least with statistics. There's going on here in partial least squares. A lot of it can be addressed without ever addressing hardcore statistics. But I decided that here I wanted to just pull out those things that connected partial least squares and statistics. So with that in mind, what did we find? What did Lily and I find? Well, for our key findings, these are the things that I'm going to be playing with as through the seminar, but I want to keep the following ideas in mind. First of all, partial squares regression, the algorithms that you find in the literature, like Nepal's algorithm or simplest, really contain two arms. One arm is the dimension reduction arm in a pretty classical sense, and the other arm is the estimation arm. Now, the code and the people that I've seen write the code don't really distinguish those two arms. They of Nepal's as mainly fitting linear models. That doesn't have to be the case. So with that in mind, most of my comments are going to be about the rhythm for dimension reduction, and not about the subsequent part of taking the results of the algorithm and doing something with them that's relevant for the problem at hand. And it's the algorithm itself that connects partial least squares with statistics. The rest is pretty routine, as far as I can tell. So you see there in the middle of the screen the kind of reason that we can go to make that connection. Least squares algorithm produces is in effect envelope method. Envelopes are a subset of sufficient dimension reduction. So sufficient dimension reduction has now been around since 1990 approximately. It's a well-established area in statistics. There are many cool methods, and partially least squares regression, the algorithm, it seems, another one of those methods that can be associated with sufficient dimension via the link on partial regression. The algorithm came in around 1980. Until 1913 that went on about that we had the link to establish a connection between partial least squares and sufficient dimension reduction. As I've already alluded, the linear regression is not required. For example, the PS algorithms like the simplest and like Nepal's and simplest, they can be just as serviceable in linear regression as the linear regression. So the reduction aspect of partial least squares is what intrigues me. To accomplish the dimension reduction, the is, as I mentioned before, fairly routine as far as I can tell. Collinearity, partial least squares is unencumbered by collinearity. That's a property that's really inherited from envelopes. If you have a clear problem, the sample size still being substantially larger than the predictors, partial squares can perform much better than linear least squares, even if the sample size is greater than predictors. So we find that partial least squares there is a for it, particularly in problems where there is some notable degree of collinearity. Now, point number 4, regardless of the relationship between n and p, its estimators, the partial squares estimators, can converge at the root n rate, provided the signal is sufficiently strong. This is was an interesting thing, because for 2 decades now, the statistics community has embraced sparsity as a way of handling high dimensional problems. You see some people say things like, well, if it's high dimensional, it must be sparse. And if you don't assume sparsity, there's not a lot you can actually do. That turns out to be not the case. Here, partial least squares can converge at the root n rate. That is, the goodness of your estimator is controlled by the sum n, regardless of the relationship between n and p. So n 100, p 1000, and still expect to get goals in the right kind of set. And these are settings that I think are pretty much characterized by the kinds of problems that you encounter in chemometrics, and in other cases as well. Oops. The final statement here, I think, is what is worth thinking about. The overwhelming focus on sparsity in the statistics community has, I think, roadblock to thinking of alternatives. One of the things about statistics is when you encounter a particular problem or class of problems, there are usually different ways you can go, and you can pick the way that you seems most relevant for your particular problem. But for a long time, at least in frequentist statistics, if it was high dimensional, it had to parse, and there were lots of clever ways of producing sparsity to various kinds of ones. Now no longer think that sparse is necessary in that regard. PLS is some turn my thinking around to say sparsity is a reasonable method, a reasonable assumption, but it's not the only assumption. And perhaps seeing that sparsity isn't the only assumption will allow us to open the doors to finding many alternatives to high dimensional problems. So those are 4 things I pulled out that kind of connect partial squares with statistics. Now let's for the little background. Partially squares. Some people like to interpret P not as partially squares projection onto latent structure. They tried to rename it because they think projection onto latent structures is more accurate. And in a sense, that's right. Historically, I don't think there's going to be any hope in changing the meaning of the acronym PLS. There are many kinds of PLS methods. Partial least squares regression is just one of them. It's in the PS family of methods, but the emphasis here is that PLS and PLS regression are not synonyms. Partial least squares sort of stand. The whole family's partial least square regression is a particular class or subclass of that family. Nevertheless, during this talk, if I speak of PLS and I leave off the word regression, you can insert the word regression for me, and I will thank you for that. Partial least squares goes back to the Herman Wold. He had his PhD in 1938. Harold Kremer was his advisor. He'd made important contributions across the field of statistics. Perhaps most of us are most familiar with the Kremer-Wald. Students should be familiar with that theorem. When Wald was working on his algorithms throughout the 60s, before partial least squares regression was even considered, we have to think about or remember what it was like to do computing in the 60s. Chances are either using in the 60s decks of cards to do your computing. It was incredibly slow to try and be very, otherwise your program might not work. Or in the early 70s, they switched to paper tape as a different way of storing your code. This was a different time. Computing was in its infancy, and it was really quite difficult. One of the reflections of it in the code for Nepal and for Simplest, the versions of that code, if you try to, it seems to very figure out what's going on. Part of the reason is that now do today with a single in a language you had to do by yourself in the 60s. The Nepal's algorithm relies on being able to compute the eigenvector associated with the largest eigenvalue matrices. There wasn't routines for doing that. Usually the routines were built code, and that's a characteristic of early versions of Nepal's code that have gotten forward. So reading that code is really is a task. Regression algorithms were introduced about 1980 by the Scandinavian chemometrics community, and by 2000 it had become a core method of chemometrics. And this is where a lot of our information about partial least squares come. The people I think of when I think of the early work in partial least squares are Herman Wold and his son Svante, Harold Martins, Tormod Naes, and Inge Helland. The small footprint in statistics, and I've listed several there. It really didn't catch on in statistics. Papers would be published, and they wouldn't seem anywhere within the statistics community. It was kind of hard to figure out why that was the case. And one of my conjectures is that during this period of the rapid development of PLS regression, we still hadn't come to grips with the idea of algorithms in statistics. We were still mostly models. Models allow a lot of things with relative ease, prove basic properties of layers. It wasn't 2001 when Lehman published his paper on papers that things began to change in statistics, and we began to recognize algorithms as a legitimate way of doing things. A lot of people have written about the difference between the statistics and chemometric cultures as illustrations of Ryman's two cultures. Helland, for example, asked the difference in terms of creativity versus rigor. The people in chemometrics being the ones, and the people in statistics being the rigorous ones. I don't know if I agree with that, but nevertheless, there's been a lot of discussion of that. So that's how things were for me. I wasn't really paying attention to partial least squares. I hear about it once in a while, but I mostly dismissed it like all of my colleagues. And that carried on until Helland in 2011 spent a semester at Minnesota. And one day Inge and I were discussing partial squares, and I was asking questions about it. It turns out that through arguments we had conjecture that there should be a connection between partial squares and envelopes. And that is what gave rise to the first paper that had first connections between partial squares and envelopes, and that's Cook, Hilland, and Sue in 2013. So let's now go into a little bit more detail. In this, I'm going to be about PLS algorithms for regression, regressive response on a p-by-1 vectors. I'm staying with a response here rather than going to vector because.
Dennis, just a second, because there is a lot of echo, and I'm not sure what to do about that, because people are complaining in the chat, and I'm not sure what we can do about that.
Lily, I think you can try to mute the microphone that you have in that room, in the seminar room, because
I have it. I have it.
It's muted. Okay.
Because
otherwise,
in his audio, maybe he can do something in his audio like configuration, but I'm not sure what to do. Do you know what to do, Francesca?
I was saying that my suspicion was that there was a microphone open in the room where you're gathered. So online we hear both from you and from Dennis, but this is just a suspicion. I don't know if this is what's going on.
I could mute my microphone. Would that help?
No. Okay.
What to do, Lily? We played
Maybe
with this.
Dennis, maybe if you mute your speakers, maybe that would help.
Well, let me get back to the controls here. Speaker should. I'm at a loss of what to do.
Not sure. When you have the headphone, we can hear you perfect, but you couldn't hear us. Maybe you can give a talk, but you don't hear us, and then you change. Because when you had the microphone, we could hear you pretty well, but you couldn't hear
Okay,
us.
let's try that.
Let's try that.
I'll try that.
And we make signs.
Although. Can anyone hear me?
No, yes.
Where? Francesca, I see you. So if you can give me a thumbs up. Okay. Lily, since we can't communicate, you could send. I don't want to bother with the chat. If there are still problems, send me a text. I've got a phone here. I can put that quickly.
No, Dennis, we can still.
Okay. Since you couldn't hear me before, shall I go back to the beginning?
No, no, it's okay. We could hear you. It was
Francesca's
just
saying
with
yes.
an echo.
Okay. That's a good place to stop and try that fix. So PLS algorithm for regressing a real response y on a p by y1 vector x. Why real? Well, it's because all of these algorithms work for a multivariate way, but simplest and the Paul's algorithms give different answers. I don't want to get into that in this seminar. It's just a quirk. Asymptotically, they agree in the population, but in finite samples, they give different answers, and trying to tell out why they give different answers is not something that I want to do here. So we're going to stay mostly with the real response. Some of the results I'm going to show you also apply for vector valued responses, and I will hit that at the appropriate time. So the data we're going to assume we have independent observation on the pairs y and x. A little obvious notation there. One of the things about partial least squares regression that's different from most other regressions we do in statistics is that x, the distribution of x, is not ancillary. The distribution of x matters in least squares. If we condition on x as traditional in many statistical analyses, we lose information that partial squares uses. So x must be random, and it's going to be random from here on. The goal of partial squares is to compress x into transpose x without loss of information on y. W is a p by q matrix. Q is less than or equal to the minimum of n and p, hopefully a lot less, and q the number of components. Try and remember the components because that's going to be key. We're going to be talking about that frequently as we go along. Here's a bare bones version of the Nepal's algorithm. I don't see this any place other than in our book. It took a little bit of effort to condense this down to just the essential part of the algorithm, and here it is. You can scan the top of that for notation. You'll notice I've divided this into two parts: the dimension reduction arm, which is the one we're focusing mainly on in this talk, and the estimation arm. The first thing we do, what this algorithm does is it builds up W. Remember, we want to compress x into W transpose x. It builds up W column by column. The first column of W is the first eigenvector of the covariance matrix of xi times its transpose, so the outer product of that covariance matrix. So then we W1 equal to little w1. We've now got one vector. To get the next vector, we have to do two things sort of simultaneously. First thing we have to do is get rid of the vector W1 when we already have. And we do that through this projection. One projected out, this W1 corresponding to WD, and this is the projection in the sigma x inner product. We again form the outer product and get the next largest eigenvector, first eigenvector, that gives us the next vector in W, win that to W, and we continue until we stop, and that gives us x maps to WQ transpose, where Q is the number of component. It's the number of time iterated through this before we stop. Now, when do we stop? Well, there are many different ways of stopping. Q is determined in regression problems by cross-validation. It can be determined by a hold sample, or we can stop when this particular matrix here is less than a user-selected bound. In this algorithm, I've written in terms of the population, but for sample versions, just replace the population matrices with sample matrices. Now, the reason I've emphasized this one is because it turns out that there is a close connection between the partially squared algorithm and the conjugate gradient algorithm that's used, for example, for solving normal equations in statistics. And this is what you use in the conjugate gradient algorithm for a stopping point. But if you're doing statistics and you're, for example, fitting a linear model, then you can get Q by cross-validation. If you now think you're going to be fitting your model, then in the estimation arm, you can simply form this entity, and that gives you the estimate of data. Again, these things are essentially distinct. Once you use this, there are a lot of things you can do with it. You're not obligated to do linear regression. Here's the promise. There's a little data that I've shown in talks before, but it kind of illustrates what you expect and what you hope to happen with the least squares. So here we're predicting protein count of beef based on some measurements at 50 wavelengths. We have 103 observations, and we're going to use five-fold cross validation for root mean squared error prediction. The blue line is partially squared, and the black horizontal line is ordinarily squares. So this line, horizontal line is ordinarily squares. That's the prediction error for ordinarily squares. The dashed line, the prediction error you get from partial least squares, depending on the number of components. So the number of components here, you would like to pick ideally with 3 or 4 or 5. Doesn't really matter. It's forgiving in this area. You certainly want to stay away from like anything greater than 10. But anything in here would probably give much better results than partial least squares. So that promise, whether or not promise is realized in any particular example, depends on a lot of different things, some of which you'll have control over and some of which you won't. So understanding PLS versus envelope. So what I've just done is give you a brief overview, sort of a feeling for what PLS does and what its potential is. And now we're going to reintroduce that by envelopes. To do what we're going to do is do a comprehensive model-free treatment, and we will gradually work back to linear models and PLS regression. So here's some overarching ideas. This is now starting fresh. We're going to go through a number of steps, a number of ideas, and a number of logical reductions, and then we will end up with PLS again. So PLS strives to compress X into W transpose X without loss of information on Y. Statistically, we express that as Y is input of X given the projection of X onto the subspace spanned by the columns of W. That's not a new representation. That's the basis for sufficient dimension reduction. It came out in the 90s, and for a long time, people have been working on statements like that and similar statements, refining them, moving it here or there, the kinds of things you do with statistics to specialize to a particular problem. The span of W is a dimension reduction subspace. The central subspace, the estimated target for sufficient dimension reduction, is the intersection of all matrices W of spans of W to satisfy this equation. So in that sense, you pick the smallest W and try and estimate it. Now, again, there's a lot of work in this area. It's not all the central subspace, but it all back to the central subspace at the beginning. What are the issues here? Well, the issue we're going to think about now is collinearity in X. If there's very much collinearity in X, it gets extremely difficult to estimate the central subspace. And that's because it's hard to estimate this projection from its orthogonal complement. They just mixed up really easily. In fact, in the early years, when people were publishing on sufficient dimension reduction, in their simulations, they would very often X to have an identity covariance matrix, so that so that linearity wasn't an issue at all, and you got the best results. How do we deal with collinearity? Well, that's the next slide. Envelopes and PLS add the condition that the covariance between the projection of X onto the relevancies and the projection of X onto its orthogonal complement is 0. We eliminate linearity by saying we're only going to take subspaces. Excuse me. For some reason, every time I touch my mouse, this bounces. We're only going to consider subspaces where the orthogonal complement, the covariance between these two, is 0. That takes our collinearity by definition.
there's no chance you're going to get mixed up anymore because the things you leave aside are going to be correlated with the things that you're keeping. So this material information, that's what you keep. This is the immaterial information. That's what you're going to chuck. That's how we keep how these methods, envelopes and PLS, take care of collinearity. So here's kind of a summary of what we've done. The two conditions at the top, A and B, are driving conditions for envelopes and PLS. Condition holds if and only span of W contains the central subspace. Condition B holds if and only the span of W a reducing subspace of sigma x. So those two conditions together enable us to say that the envelope, which is a subspace, is the smallest reducing space, the central subspace, smallest reducing subspace of X that contains the central subspace. So it's the intersection over A and B of all span W's satisfy those two conditions. And thus we get this fundamental reason that the envelope contains the central subspace, and that's the nature of the one thing subspace with another. This is a very general statement. This kind of thinking came about only very recently. It's exactly what we need to connect PLS with envelopes. So, what is the PLS connection? In linear regression, Paul's and simplest algorithms compute estimators of this. That's exactly what they compute, and that was the result. And it opened the door for everything, and enabled us to make connections between PLS and statistics. Q now is the dimension of the envelope. We sacrifice a little bit when we do this because PLS and envelopes may give more components than sufficient dimension methods. It's because Q, the dimension of the envelope, is going to be no smaller the dimension of the central subspace. So we could end up with more linear combinations than we need, strictly speaking. The trade then is the following thinking. Like I have difficulty estimating exactly what I need. I'd have difficulty estimating the central subspace. So when I run central subspace methods, if I have collinearity, there's always this doubt, these large standard errors that cause me to know what's happening. On the other hand, if I span the central subspace to the envelope, I get really good crisp estimators. So I can have crisp estimators that are too large, or I can have estimators of exactly what I want that are fuzzy, if you will. So in the context of the linear model, the span of W hat, that W is produced by partial least scores algorithm, whether it be simple or Nepal's, is a root and consistent estimator of the envelope. That's the first time the PLS method associate with a particular demand, and that's what came out in the Helland and Sue book. So the idea that I want to leave you with is that sufficient demand reduction produces envelopes, which then produces PL regression. And you're thinking about algorithm, not particular estimate. Now we can refine things. Having that knowledge, we can refine this, and we can write a version of the linear model that specifically takes the reduction into account. So here we have y is alpha plus eta transpose w transpose x. Here's the reduction we want. Here are our regressions in terms of the regression y on w transpose x. Here's what it implies about the covariance matrix of x. It has to be that form. We're still interested in beta, which is eta, and x. They're still the things of very interest. This is now the reduction form of the simple linear regression of the regression model. The PLS regression and OBS differ on how they add W. That's the main difference. They're both estimating the same thing. They both strive to estimate the envelope or a basis thereof. An envelope for you, if we think of envelope estimation, let x, y be multivariate normal, and we go through the likelihood, we can get very good estimators. It's a job. The likelihood in this case is not convex, although we have a considerable progress in regard. The less estimator of is relatively slow to compute, and it allows n less than p. So the short story is envelopes and PLS estimate the same thing, but they have two different and distinct estimators. If you can write a likelihood function and it satisfies the likelihood and n is a lot bigger than p, you should certainly use envelope methods. But in the kinds of applications, well, we have issues might not be much relative to p, then PLS is a really viable alternative. So here's the promise. Again, promise number 2. This is the same problem we had before. The horizontal line is still OS. The blue line and here is still PLS, and now the red is the envelope estimator. And what you're seeing here kind of characterizes the difference between PLS and envelopes when the sample size is sufficient. The envelope estimator is much more forgiving in the number of components, for example. Here's another data set. This is a data set I've used in many different contexts because it's kind of you can do a lot of things with it. So this is a data set that came from a study of horse muscle sampled from the Marlborough Sounds coast of New Zealand. Y is the log of the muscle's muscle mass. And one of the reasons I like this example because it's kind of fun to say muscles. There are p equal to 4 predictors. They are the logarithm of shell height, shell width, shell length, each in millimeters, and mass in gram. There are 79 observations. When we read through the analysis, there was a really strong inference for one component, Q equals 1. So here, n is quite larger than p, and so we can look at a diagnostic. Here's y is the PLS values on the horizontal axis. We have a nice straight line. There's no indication of curvature here. It's the kind of plot you would expect when everything is going well. Here is a plot of the OLS fitted values versus the PLS fitted values. You can see they're virtually identical. So one might think, well, fitted values from OLS are virtually identical to the fitted values from PLS. Why do I need PLS? Why can't I just use OLS and be done with it? Well, the answer is because PLS gives you a much better feeling about the accuracy of your estimators and gives you much better estimators. Here's the difference. The first pair, error estimate and standard error, are the usual OLS estimates or estimates. The second block are the PLS estimators and their standard error, and the third block are the envelope estimators and standard error. You can see that the PLS and envelope estimates are really quite different from PLS estimates. But the difference is sort of within standard errors. If you look down here, 206 is certainly reasonable given that pair. You looked at the OLS analysis, the traditional way, sort of the textbook way you would teach students, you would say, well, it looks like we have a lot of predictors here that might not be necessary. The only one where we have a clearly important predictor would be beta 3. That's standard. This est is less than is greater than twice. That's standard. But the rest are iffy. So you might delete one, rerun the regression, and see what would happen. That's a common kind of thing to suggest to students in regression class. On the other hand, for partial squares, the estimates are really seemingly different, but the standard errors are what catches your attention. they're incredibly small relative to the size of all of the tests. PLS says, well, you really need all of your variables. Once we get rid of the imageable information predictors, we that away, hey, we have very, very strong relationship, and you need all of the variables. Going to envelopes, we see the envelope and PLS estimators are really close. Standard errors, however, just a little bit smaller than the PLS standard errors. 6.352, 6.756, and so on down the line. That's kind of what you'd expect as asymptotic. Using likelihood, the envelope estimator should be best, but those kinds of differences in standard errors probably aren't enough to get you excited. But these kind of differences in standard errors, OLS, these two, is enough to get me excited in any event. So even if your fitted values turn to be really close for all three of these, the intricacies analysis suggests PLS and envelope much better ways to proceed. We can go on a little bit from here. There, Rill and others in 2019 published a paper called "Comparison of Response Prediction Method," and I've extracted a bit from their conclusion section, and I'm going to read this because I think this is relevant. Analysis using both simulated and real data has shown that envelope methods are more stable, less influenced by a predictor collinearity, and in general perform better in principal component regression and partial least squares regression. These methods are also found to be less dependent on the number of components. Well, we saw a little hint of less dependence on number of components in the motivating example I gave, but the reason this is important is because here are three people publishing in chemometric their contrast envelopes versus their methods, and they admitted that envelope better. They have nothing to do with us. I did not know this study was coming out, and yet here it is. Of course, pleased with the results. So it's sort of independent information of the value of envelopes. Now, they did something that I'm not quite sure what to make of. When n is than p, maximum likelihood envelope methods, which is the only ones that are available, don't work. The likelihood simply doesn't exist. You can't do it. So what they did was they did a common chemometrics tech. They said, well, when n is less than p, we're going to use PCA to reduce the predictors prior to applying likelihood-based envelope methodology. So they reached the predictors and got the predictors less, the number of effective less than p, stood into the envelope methodology, and we still won. That is, envelope still won. I'm not quite sure what to make of this. I can really write examples where methodology will fail miserably. So I think what's happening is there is something special about chemometrics data where this would be a reasonable thing to do. But in general, I'm not sure reasonable thing to do. So there's still work here to try and figure out how to handle or how to apply envelope methods when you have n less than p. It's that I'm not characterized as sparsity. You might not be sparse at all. So there's still questions in my mind about what to do there. Nevertheless, this still strong for envelope methodology. So asymptotic performance of PLS. Now we're going to switch gears, and we're going to think of PLS just for the PLS. And I want to talk about the asymptotic performance. What happens to PLS estimators as n and p go to infinity? This is the common way statisticians have of sorting out high dimensional problems when p could be an n. So what we're going to do here is we're going to look at some results that Lily and I have on the same linear model context, we're going to assume x and y multivariate normal. The number of components, that is the dimension envelope is fixed, and a few mild regularity conditions that I'm going to talk about. And what we want to know is what happens as NP go to infinity, assuming that the variance of y given x is bounded away from 0. That's kind of a technical assumption that I think is relevant when you're thinking about asymptotics. Technically, I could say that the variance of y goes to 0, and that would lead you to a entirely set of results. We're bounding the variance of y given x away from 0, so you can never know exactly what y is from the values of x you had at hand. So I'm only pulling out part of the results. There's a lot of nuances going on here. This is the height. This, to me, is what I remember when I have asymptotic results for partial least squares. So the signal is going to be characterized by eta of p, which is the trace of the variance of W transpose X. We're going to think of that as the signal. We like that to be large. What we're going to measure is the orders of this quantity. So given the fitted value for a new value of X, how does the fitted value tell us about the mean at that new value X? And how does the TLS estimator of beta tell us about beta in the sigma X inner product? So those are the orders. It turns out these two things are the same order, so we don't have to separate them. The order apply to both of those things. And it gives a pretty idea of how you expect things to work as n and p get big. We're going to model the signal as being asymptotically equivalent to p to the t, where t is in 0 and 1. This is the general result. I'm not going to spend any time thinking about the general result. I want to talk about three special cases. If t is equal to 1, then the sig is asymptotically equivalent to, which means that most predictors carry information about y. As you add predictors, most time you're going to be accumulating information about y. If that's the case, then you're going to converge at root n rate. That's a traditional statistics rate. Everyone strives for that kind of rate. And if you have an abundant regression, which we think of here, abundant because signal is abundant. Any predictors tell you about the response. You're going to have very, very strong results. If t is half, so you have 100 predictors, you would be thinking about, maybe 10-ish digits relevant. If 10,000 person predictor, maybe like 100 of them are relevant. So t is a half means only part of the predictors are relevant. How does it fare then? Well, then the convergence rate is square root of p over. So you have to have n larger than the square root of p. If p is 10,000, then n of a few hundred would probably be 9. So you have n of a few hundred, p of 1,000, and if t is a half, you would still expect to get sensible results. The last one is t equal to 0. If t is 0, it says the signal is constant. Asymptotically. What that means is that only a few of the predictors are contributing information. As you accumulate predictors, you necessarily accumulate predictors that are giving you information about the response. That's sparsity in the usual sense. Then you have to have p over n small. That's the traditional way of thinking. The number of observations is going to be large relative to the number of predictors. So this is really the only case where partial least squares we faced with the usual kinds of restrictions. These two cases, t between 1 and a half, for example, partial least squares should work really well, even if p is quite a bit larger than n, provided you have this kind of relationship. So I think partial least squares is a very reasonable technique to use if p is bigger than n. Here we have the case where the convergence rate depends only on the size of n. Here has to be large relative to the square root of p. These are very strong results, and actually I can't think of any other place, there may be, but I can't think of any other place where you would get these kind of results as n and p go to infinity. So the informal conclusions here are that if the signal is bounded, that is, we have sparsity, then the standard PLS methods may not work well in high dimensional regions unless n is bigger than p. But there are sparse PLS methods available. Zhu and Su in 2020 published a paper along those lines of panels. Here, we're not talking about PLS methods, but the basic PLS methods like Nepal's and simplest. If the signal is unbounded, abundance, then standard PLS methods should work well. In fact, when least squares was being developed, the Wold, Herman, and Svante argued that you shouldn't be deleting a lot of predictors, that most of the predictors are going to give you some information about why, and that you should keep them. They didn't use the word abundance, but that's in effect what they were arguing for. So that's a little bit on asymptotic results via consistency. Here is another set of asymptotic results that talk about the distribution of P transpose times the partial least estimator of beta. You have a single component function. G is non-stochastic, it's selected by the user, and otherwise the same linear model context. We really have two sets of results under varying conditions. Under a set of conditions that we'll talk in a minute, it's quantity converges in distribution to a standard or normal. Now, this is a scaling constant. Familiar with scaling constants, and in the book papers, these things are written out in detail. I'm not going to give them here. The thing that I want you to notice is that there's a bias correction that that is necessary to get to be normal. If you don't do the bias correction, you're going to have bias in your estimators. If we add more conditions, if we make it stronger, then the bias go away, and we can get that this thing goes in distribution to a certain normal. Here's what it looks like in detail. If t is equal to 0, still modeling the signal as p to the t. If t is equal to 0, bias estimator converges if n to the 3/4 is bigger than p. The usual estimator converges just to the standard normal if the square root of n is bigger than p. That's a really strong condition. So if you have sparsity and you apply PS and you think of a linear combination of the betas, you can't be trusted using an inference about that unless the square root of n is larger than p. P is a half, this condition gets better, and if p is 1, this condition gets worse still. And in fact, here, if t is 1, you have the usual square root of convergence that we talked about before. Now, here's a little equal. I'm taking n to be p divided by 2, so p is twice n, 500 reps, g proportional to beta, t is a half, this one reduces to p to the -4th. Here we're not going to get any convergence, and here this is p to the -4th. So the blue will, I know your results now, the blue is going to be converging, the red should not be converging to the standard normal. So there are the results. Here are simulation, remember, 500 replications, p is 8. There are the results. The middle curve here is the standard normal. This is the red curve. There's a blue curve. Yeah, there's nothing really nice about that. Is 16. Is 32. 64. 128. 256. 512, 1024, and by the time that we get to like 2050 for P, we get pretty good results. The blue, that nicely is the standard normal. The red still is like the standard, and it will never be. So you can get full results here, but you have to be a little bit careful. PLS for nonlinear regression via envelopes. So what I'm doing at these various points is I'm not going through any of these things in great detail. I'm going to give you a flavor for what's in the book, so that if you're interested, you can go read more about it. And the flavor in number 6 is PLS for nonlinear regression. If you wish to gain information about the conditional mean, y given x, which is unspecified. So we're doing nonlinear regression. The conditional mean we're supposing is not a linear function of x, but don't know what it is. Standard PLS regression estimators and Paul's are serviceable in this setting. This is widely known in chemometrics. We'll discuss it in 1999. And since then, there have been lots of different prescriptions for doing this, for applying PLS regression in nonlinear settings. Now you notice here, I'm not referring to estimators. I'm referring to the algorithm. So this is the full iterative PLS, and of course it isn't going to work because these algorithms assume linear models when they give you the estimates. A proliferation method follows and continues today, and it was never clear. I've read many papers on nonlinear PLS, and it was never clear why the PLS regression algorithms fail. They just didn't work well. So our main conclusion: under modern regularity, the dimension reduction arm PLS algorithms used for linear regression is serviceable for reduced dimension in the conditional mean. You just do exactly the same dimension reduction algorithm, and instead of using linear regression, you now have a conditional mean that you're trying to infer about. So that is, PLS compression is suitable in nonlinear regression just as it is in linear regression. In linear regression, once we get that, what we would fit is this, using PLS. In nonlinear regression with additive error, we use the working this. We don't know what that mean function is, so we have an off-the-shelf method. There are tons of off-the-shelf methods for inferring about a mean function, particularly when the number of vectors is low dimensional. So if you're successful getting this down to a low dimension, if Q is like 2, 3, or 4, there's a whole range of additions of method statistics that can be used to infer about that entity. Here's an example. This is the Decatur data from Shan and others in 2014. They looked at root mean square testing errors for 6 nonlinear PLS type methods of predicting the position of meat samples. There are 72 samples, 43 testing samples, P100 spectral predictor. So they have basic PLS method. Here are the root means for predicting fat, protein and water. Something called quadratic PLS. These are all methods that have been proposed in the PLS literature. Kernel PLS, located PLS, PLS polynomial. You can see they kind of get better as you go down. And then PLS sliced transform, they're better still. Well, better still. It's in blue because that's the method that Shan and others proposed. That's the new method in there, and they said, look, this method works better than the others. Now, PLS slice transform is a method that is very, very set to sliced inverse regression in dimension reduction. Nevertheless, that's what they came out with. So what Lily did was we used PLS, the dimension part. PLS algorithm dimension reduction, we took the reduced predictors, just like you would in linear regression. Then we reached into the literature and we pull out a method that one of my students, Kofi Drogny, and I proposed in 2009. We didn't spend anything picking the methodology. We just said, well, PLS dimension reduction, and now pull an off-the-shelf method. And of course, when we went shelves, we went to my shelf. Here are the root mean square prediction errors. 1.4, better than all of them. 0.54, better than all of them. 0.32, better than all of them. So we didn't mess with the algorithm at all, the dimension reduction algorithm. We kept that exactly the same. We got the predictor dimension down, and then we used an off-the-shelf statistical method. And it worked better than six of the methods that are proposed to handle nonlinear PLS problems. Here's an example. Capini in 2020 developed a neural network for online prediction via spectroscopy of a protein used in the treatment of autoimmune disease. They started with the sample size 35 and 38,500 spectral predictors. So P is really a lot bigger than N in this case. They then said, oh, really too big. We can't manage a neural network with 38,000 predictors. So they systematically reduced it to 9,300 some. Then they said, yeah, that's still too big. So then they applied PCA and they reduced the 9,340 predictors to 12. So now 12 predictors, they're hyperparameter selected via box-bend design to optimize the desirability function. The root mean square prediction error that they got over their testing samples was 8.6, and that's compared to 15.3 for partially squares regression. So they roughly have the root mean square error for partially squares regression. So what Lily did was she applied the PLS reduction method, like I showed you, same one they used for linear regression, and then we added the same parametric inversion from that we did before, and we didn't do any of the massaging at the beginning. We said, well, we're going to keep the 8,500 predictors, and what we got was a root mean squared prediction error of 8.46. So we didn't have any of this overhead. We didn't have to reduce the predictors. We just applied it routinely and did better than they managed to do. Now, I don't really recommend doing this. You probably have to be more intelligent, use characteristics of the particular problem. The message I'm getting across here is not this particular bit of methodology. The message I'm trying to get across is that that is the universal idea in partially squared. That's the method that carry you from problem to problem. What you do here, what you do after you get the reduced dimension, partially squares really has nothing to tell you about that. It assumes linear regression at the beginning, but then you can go anywhere you want. So in closing, and that's not bad for time. In closing, here are 4 books that I've listed that carry you through the temporation in this idea. There's my first book, 1998, Graphics Idea of Studying Regressions with Graphics. I was doing graphics in this, but the foundation of it all was dimension reduction. And the graphics community didn't like it, but the dimension reduction community did, and that's where it lives, in the dimension reduction community. Then second iteration, Bing 2018 published a great book called Some Dimension Reduction that carries us into the second generation of sufficient reduction. Same year, I published a book, Introduction to Envelopes, coming right on the heels of Bing's book. And now Lily and I have published partially squares regression methods that again spins off envelopes and the subsequent ones. So this is kind of the progression of how this area had progressed and embraced other methodology. Just a few common other topics covered in the book. There's PLS for response and simultaneous response and predictors. PLS will be part of X from dimension reduction, the role of partial least squares in social science math analysis, PLS for discriminances, PLS for limbs, and a discussion of PLS and the conjugate gradient of. At that point, thank you. I guess I'm going to.
Thanks so much, Dennis. I want to know if there are questions from the Zoom or from the public. Is there any question? People in the Zoom can unmute and ask questions if they want. I don't see the people here.
Okay.
Yes.
Hello, can you hear me?
Yes.
Okay. Since you've done stuff with graphics, I wonder if you've done anything with so-called virtual reality with 3D glasses.
Dennis, can you hear the question or?
No, I wasn't ready to hear it yet. I was taking the earphones off because I couldn't hear with them.
Okay.
Okay. I was saying, since you've done stuff with graphics, I wonder if you've done anything with so-called virtual reality with its, using the binocularity illusion.
No, I've done nothing with that, Michael. I haven't thought seriously about graphics for a few years now, mainly because the graphics community seemed interested in that kind of stuff.
I've been thinking. Okay.
Go ahead.
Oh, I was saying I've been thinking about doing some stuff with teaching Fourier series using that sort of stuff.
Yeah, that could be interesting.
Is there any other question from the Zoom or from here?
I can try to ask a question, and then if you probably alluded to it many times and probably is in the book, but just at some point you said that if you do PLS, you can, with this enveloping thing, you can actually get a space that is a little larger than it needs to be. Okay.
Yes.
In the other half of this world where one does feature selection with whichever method, it's pretty common to refit a model post-selection, right?
What?
How about redoing dimension reduction post within the subspace that is identified through PLS? And it actually, it's very similar to what you were doing now at the very end in some of the examples, right? So this notion.
Yeah, I take your point, and I explored that at all. I thought about that could be an interesting refinement, particularly got envelopes or PLS components. If you have 100 predictors and you end up with 20 components, maybe you only really need something like 10. And if you, within the context of the model, reduce that down, that would definitely be handy. If I understood you correctly.
Yep. Thank you so much for a great talk. I'm gonna mute myself.
I think in that case you have to do twice asymptotic because you have something in the sample and then you do reduction on the reduction, no?
Right. There are key questions there.
Yes.
But that'd be an interesting idea.
Yeah. Is there any questions?
I have a question. Yes. Hi, Dennis. This is Winky. How are you?
I'm good, and you?
I'm fine. I'm just so happy to get an email as suggesting that you are all back to your healthy self and back at work. So very happy to know that, and also have some time for this talk. So, two simple questions. The first one is a bit unrelated to your talk. You wrote so many books. Where is your book on optimal design that is in the works for 20 years or so? Is it coming at all?
Yes.
With Krish Naksheim or somebody?
Yes. Well, Yeah, it's coming in the following. Chris Knox are currently writing a book.
Okay,
Design.
okay.
It's a first book on design. It's intended for advanced undergraduates, beginning graduate students, and we do optimal design in there. So we integrate optimal design with classical design science, so every smooth and there aren't any bumps. But in terms of theoretical on optimal design, no, not in the works.
Okay. Thank you for that. Now, I do have a question that sort of relate to your talk. On one of your last slides, you talk about desirability function.
Right.
So I have a student who wrote her thesis on this topic. I just wonder, can you elaborate a bit more on optimizing the desirability function?
No, I can't.
Okay.
The reason that I can't is because the paper was vague on that aspect.
Okay, so even the paper doesn't talk too much about that.
No, they just say have this desirability function optimized it. You get the parameters for the neural network, the high parameters.
And the paper is what you cited, right? The reference.
Yeah, paper, what I cited.
Okay.
And one of the authors was here, but he left like 5 minutes ago.
Okay. Well, I think that's all I have for now. Very good to see you, Dennis. And
yeah, nice to see you're looking well with me.
Well, looks well.
Yeah, I know the feeling.
Okay. Take care.
Okay.
Thank you.
Thanks, Winky.
Yeah.
Bye-bye.
Bye-bye.
Any other questions? Okay, let's thank Dennis again. Well, Dennis, a little bit of the problem with the microphone, but the slides were...
Yeah, we didn't go too far over.
No. Okay. Are the
people in the room all students, or is it a mix of students and
No,
faculty?
there are a lot of students. For example, my student from the matrix algebra class, they were here, and some other students. No, most of them are students, let's say, from math
Okay.
and from the...
Well, I want to ask them a question.
Go ahead.
How many students they might want to go into dimension reduction related areas for addition or a master's paper?
Do you understand? I will
Raise
ask...
your head.
Just a second. I will put them. Just a second, because I want to see what camera. ¿Qué cámara está mirando? ¿Cómo hago?
Can you stop sharing the screen then?
Can you stop sharing the screen, Dennis? And then I can see the
Right. Right.
Now.
Sure, sorry.
What was the question?
Who is going to work in the dimension reduction? ¿Quién quiere trabajar en la reducción de dimensiones? Look at the just a second.
Well, let's see. I'm not.
No, because you have to stop sharing. Stop sharing.
I don't know how to stop sharing. How do I stop sharing? You're the host. You can kick me off.
It's not easy. Just a second. ¿Cómo lo?
Ahí se clica compartimos y ahora deja de compartir.
¿Saluché? No. In the Zoom, on the button, it says share. You have to stop sharing. Here in the Zoom, open the Zoom here. You see, I see your Zoom. Ese es su Zoom. Just a second. Impressive.
No, sorry.
This is curious. It should be easy, but it doesn't. There's a button on the bottom for share.
Yes. Now, just a second, I had to change the camera. It's not easy, all of this technology. ¿Cómo se llama? Now you take it. Wow. No, you have to see here. Who is going to work in dimension reduction? Can you see? No, I cannot. You have to come here because it's not easy. We have the technology. ¿Quién más? Había otra.
Pedro.
Ah, Pedro.
I want to learn from scratch.
We have two here. We have a student because he went to one of my students gave a class in sufficient dimension reduction in one of the conference, and after that they came to the class in matrix algebra that I'm teaching PCA, and he wanted to learn more about sufficient dimension reduction. Here we have one, Luis. Well, okay, other questions? Okay, well, thanks everybody for being here. The Zoom people too.
Lily, thank you for organizing this and for letting us participate. This was
Okay.
great.
Okay.
And Dennis, thank you for a great talk.
You're welcome. I forgot to mention during my talk, the addendum, that if you're thinking about a copy of the book, I recommend 3. One for home, one for office, and for your car in case you get stuck in traffic.
Yeah. Excellent.
Where are you, Dennis? In St. Paul?
Yes, I'm in St. Paul.
Oh,
My home.
I was even more impressed. I thought if you're in Argentina or somewhere like that.
No, we never.
This is a high-tech
we never
production.
brought me here. No.
Okay. Take care, everybody.
Okay,
Bye-bye.
see you.
Thank you so much.
Bye.
Take
Yeah,
care.
bye-bye.